Okay, I'm going to be covering balls today. Covering balls. So, when we talk about balls in math, and more specifically analysis, we're covering it here in calculus, just because it will be useful for when we deal with derivatives in higher dimensions. And I'll explain why later. So when we talk about like balls, it has to do with sets. So we should know what a set is. We could let U be a set of Rn, or maybe just R, and we define it by saying X in R such that X is greater than 0. So then U would be the subset of R such that all its elements are positive real numbers. Okay, so that's what a set is. When we get to like a ball, there's a few ways to denote a set. You could have this, and then etc. for the positive integers, or you could do X such that X in Z such that X is greater than 0. So these are the same set. You could also, actually you couldn't, but if this was the set from before, then you could denote it as this. Okay, so these are all different ways to denote a set, just different notation. For our purposes, I think this one is the most useful because it'll be the most clear. So the first question we have to ask is, what is a ball? And why a ball? So what we can do is start out with a number line, just working with one dimension, and on this line we could have 0, 1, 2, 3, and so on, and the other way too. -1, -2, -3, and so on. Now, if we have an interval, let's say -2 and 1. Notice my parentheses. This means, remember, this is another way to write a set. So this is a set, and it's the set of real numbers starting at 2 and ending, -2 and ending at 1. And because they're these, that means that these endpoints are not included in our line. So we would draw that with a circle at both, and then a line connecting our two circles. So this would be that set. Now, of course, if I instead drew this with brackets instead of parentheses, then the circle would be colored in. Because in this case, the endpoints are included. So, if we have -2, 1, very important. This one is open, and the one on the right is closed. And we will get into more depth on these very soon. But this is open, this is closed. Cool. I think we already knew that. But there's a distinction to be made. If you had -2, 1 like this, this is neither open nor closed. Neither open nor closed. And it's the same with this. So both of these are neither open nor closed. Another example, let's see, I forget how the infinity works. I mean, you can check his notes, what he did in class. Okay, A comma infinity is open, as is negative infinity B. Okay, these are also open. But if one of these were square, then it would not be open. And note here, just because it's not open doesn't mean it's closed. So a set can be neither open nor closed. And in fact, that's actually the more likely case. It's a rare property for a set to be open or closed. Okay, so back to our number line example. This was, here it's closed, -2, 1. Okay, so what I want you to do, and this will make sense for the second dimension, what I want you to do with this set is imagine that there's like a circle that goes around here. But of course, this is just the first dimension, so our circle would look something like that. Or I guess because it's closed, maybe something like that. But imagine this being like a circle. And the end of the circle are going to be, they're going to land on our endpoints here. So these two would be edges of the circle. And if you take the average between these two, which falls right here, this is the center of the circle. In other words, the circle is centered at 0.5. And it has a radius of 1.5. So this information is so important that we gotta write it down. So it's centered at oh, sorry. This should be a minus. Okay. It is centered at negative 0.5. And the radius is 1.5. Radius is 1.5. So this is something we really care about, and how we denote that I will get to very, very soon. Okay, so what next? Well, I'm gonna bump us up to the second dimension. Our X, we have our Y. And now, our set is no longer just a subset of R, it's a subset of R2. So this means it's going not just to contain like single numbers, but actually vectors. So I don't know, 1, 1, 1, 2, etc. So the elements of our set, we just have vectors instead of the single numbers we had before. So we have, yeah, vectors. And so this whole space, I'll use orange. This whole space could be our U. So whatever is orange is our set U. And it could be, you know, whatever. And then yeah, I think you pick a point in U. So you could pick like this point in U, and you could call it A. And A is in the set, but also you can have a ball or a circle around A. And this can actually, can't draw circles, but this can actually get pretty big. I'm trying to have this circle centered as A. Okay, that's not very good. Okay, assume this is good. Now what I want, this will be our radius R. Notice how it's just brushing up against the edge of our subset U. This is important. This is the biggest it can be. This is the biggest the circle can be without going outside of the subset. We care about this, and I'll explain why we care about this later. But notice something interesting. We could pick an A that's even closer to the edge of the subset. And it's still inside of it. And when we draw our circle, there's still a circle that's centered at A that's going to have some radius. In this case, it's really small. Some radius. And the edge of the circle is still within the subset U. Okay, but notice, what if I choose my A to be on the wall of the subset? Well, if you try drawing a circle around this, no matter how small the circle is, there must be some of the circle that is outside of U. Okay, so if no matter how small the circle is, if no matter how small the circle is, it still lands some of it outside U, that means A must be an endpoint. So A is an endpoint of U, meaning it's like on the edge. So that's a little bit of an explanation, but not completely. I guess I'll go over the notation. So you can use interval for this example. You can use circle for our two-dimensional example. You can use sphere for our three-dimensional example. But as you go above 3 dimensions, you're going to run out of shapes. So to get around this, we just call it a ball. And remember this information? Well, we're going to make use of this. So we write a B. It stands for ball. We're gonna denote where the ball is centered at. In this case, it's -0.5. So we're gonna write negative 0.5, and then keep it contained. So it's kind of like a function. Kind of like a function. You have this ball function, and it kind of takes in an input of negative 0.5. Now, the radius, we squish it down here. So the radius was 1.5. So we would write 1.5 down here. So to clean that up a bit, b sub 1.5 and then negative 0.5. And this means the ball centered at negative 0.5 with radius 1.5. And this tells you everything you need to know about this. It tells you where it is and how big it is. Which is why this notation is important. Okay, so that's the notation. Let me think about what I want to cover next. I guess we go back to open and closed sets. So let's say we have our subset U again. So U in Rn, whatever. And let us suppose that U is closed. Then, to use kind of the interval as an example, this means that there are kind of endpoints, and the endpoints are it's the outside. Using an interval doesn't necessarily transfer well to higher dimensions, but for the intuition, it is sufficient, I'd say. So you can imagine this, imagine this to be a ball of its own, and more like a balloon. So with a balloon, you have the rubber, which is this part, and you have the inside, which is the air. So there's the air of the balloon, and there's the rubber of the balloon. And so, when we say U is closed, that means U includes the rubber of the balloon. So that means that the whole thing is in U. The whole thing is in U. So the rubber and the inside, all of it is contained within U. Okay, if we go back, now let us suppose that U is open. this means that U does not contain its endpoints. And in this case, the endpoints was the rubber, the outer shell of the balloon. So if it doesn't contain its endpoints, but it still contains this inner bit, then it's open. You could use the analogy of like a fence and a yard. If you own this property and you also own the fence. So let's say you own the yard. This is yours. It belongs to you. If the fence also belongs to you, but nothing passed, so if the yard and the fence belong to you, then this would be closed. But if only the yard belonged to you and the fence did not belong to you, then this would be open. So if the set owns the rubber of the balloon, if it owns the fence, then it would be closed. And if it does not own the fence, then it would be open. And so, we call the yard the interior, and we call the rubber, we call the fence the boundary. So, to be more rigorous about this, a set is open if it contains none of its boundary. And closed if it contains all of its boundary. So basically, if you own half the boundary, then it's neither open nor closed, because you own some of it. You would have to own none of it for it to be open, or all of it to be closed. Right. To be even more rigorous, this is a good spot. To be even more rigorous, we say that, hang on. Okay. We'll go back to our subset U in Rn. Okay. To define an open set, a set is open if no matter what point you choose in the set, if you can make a ball around it that stays within the set, it doesn't matter what the radius is. If you can make a ball around it that does not go outside the set, for any choice of A, any choice, it could be here, it could be here, it could be here, it could be here, it doesn't matter. If you can make a ball centered at that point with any radius you'd like, that still falls within the set entirely, then by definition, the set is open. Because, well, let's say the set were closed. Well, if the set were closed, that would mean that it contains its boundary. So it owns the edge. Meaning I could put my A here. And now, no matter how small I make the ball centered around A, it must go out of U. It must go out of U. It has to, because you put it on the edge. So if the set contains any part of its boundary, any part at all, then I could put my A there and say, aha, now you can't make a ball that stays inside of the set. So if it owns any part of its boundary, then it is not open. But it's also not closed. To define a closed set, it's important for the complement of that set. So we let U be a closed set. Now this implies from the definition, let me just write this. So it's closed if the complement is open. So if Rn minus U is open. So I guess this is actually backwards. We should write it like that. So the definition of a closed set is a set such that its complement is open. Meaning, let's say you have an open set. This is your open set. I guess with dotted lines instead, because it doesn't own its boundary. If this is an open set, mainly talking about this. So if this is open, then you think about everything that's not this, which would be, you know, all of this. I'll use blue. All of this would be a part of this. And because the open set did not contain the boundary, then the complement to the open set would contain the boundary. And so because it contains this boundary, then it is closed. Because it contains all of the boundary. There are no gaps. There are no parts where it's dotted. Yeah, I hope I did a sufficient job. It was a little longer than I wanted it to be, but I think that should be good for balls and open and closed sets.